So this is 1 meter long. And today, these blades are somewhere between 45 and 50 meters long, each blade. And so that's 150 feet, 160 feet. So the diameter of the rotor, right, is 300 foot easy, 400 feet easy on some of these wind turbines. And, you know, they work just like a propeller on an airplane. Because they rotate a little slower on the inside and a little faster on the outside on the tip. So it's, when you make these blades, when you design them, it's just like designing a B-52 bomber here and a jet fighter here, and you have to blend those aerodynamically because when it rotates through the air, this tip rotates at 140 miles an hour, and this in here, well, if it's 8 RPM, it's not very fast, right? It's 20, 30 miles an hour. And so a lot of engineering goes into just the blade alone. And they pivot in the wind. The higher the wind speed, the more you want to pivot these back so that you don't make too much power. So that's the difference in size here. This is 1 meter, so it's 1 to 50 exactly. So to make these blades, you make a mold. You basically split this blade down the middle here, and you have the one side of the blade on this mold and the other side of the blade on this mold, and then you put a like a shellac for your nails almost down, and that's the gel coat, and that's where your paint is as well. Some people paint them afterwards. It's sort of all depending on, you know, who you are, if you're Vestas or Siemens or GE. But then you start laying up fiberglass and carbon fiber, and once you've laid that all up, it's wet, just like when you have to patch a hole in the drywall. It's a fiberglass mat that you're using, and you lay that up and you press it down, and you have these spars on the inside, just like an I-beam, that makes sure that this blade, which we just talked about, right, it's 150 foot long. Some of them 300 foot long. If you have to hold on to that here, it takes a lot to hold on to that blade out there. You have to have, they call it a spar cap. You have to have these structural pieces inside of the blade to make sure that they don't flex too much. They have to flex a little bit, because the higher the wind is, you want to flex that blade backwards just a little bit, so that the load, if there's a gust of wind, that load is absorbed not by just speeding up the rotor, but by flexing the blade back. Because when that load then retracts, when the gust is over, the blade will want to come back and want to speed the rotor up just a little bit, and then we're ready to harness that wind out of the turbine as electricity, instead of having to put the load from here down to the ground where it's wasted. We pull it up in rotational energy instead. In the wind, they actually flex like this because the wind load is so heavy on them. So if you paint them a different color than white, one side of the blade would heat up more than the other, and you'll start getting an expansion on that side, and therefore a wrong twist, and therefore it messes with your power production and your basically your stability of your turbine, your natural frequency. So yes, you can paint them whatever you want, but you have to do a lot of engineering. It's a big theoretical question. Efficiency-wise, a two-bladed wind turbine is almost as efficient as a three-bladed wind turbine. A one-bladed wind turbine has the efficiency of one blade.
Okay.
A turbine with two blades doesn't really double the power output, and a turbine with three blades doesn't triple the output. However, for dynamic reasons, two blades, you can imagine, as you go up in height, the wind speed increases. And so you have a turbine with just two blades. That one blade will come up into the air and speed up, whereas this one is all the way down there and wants to slow down. So you're seeing this rocking motion of the main shaft all the time. And think about it, the main shaft in here is 5-6 foot in diameter, and it is 6 to 8 foot in length. If you have a two-bladed wind turbine, you can actually see that axle bending, and it's not hollow, it's a solid axle. So there are so many forces at play here that a two-bladed wind turbine, although it's very efficient, requires you to have a pivoting hub and requires a lot of mechanical, technical things in order to make it work right. Whereas this, when you have the one blade up, yes, the wind is still higher up here, and it wants to speed this blade up. However, you have two blades at the bottom that makes up for that that rocking motion you otherwise would see. And then once you have these two blades, they're not quite at the top level, meaning you're slowing the rotor down just a tiny bit, but not as much as you would if it was just two blades. Now, offshore, where the wind speed going up, you don't have what's called shear, is not as high as it is on land because you have shear, because you have all of this roughness, that's trees and buildings and hills and what have you, that slows the wind down. So you have these boundary layers. You don't have that on offshore. So offshore, there's actually work being done right now in these massive two-bladed wind turbines because they don't have that rocking motion, because you don't have the difference in wind speed up and down the rotor. What we call the rotor plane is from this tip to where it would be up here, which is also what we call the rotor diameter.
Wow.
So it is generally a faster wind speed. It's just not a difference in wind speed between the lower blade and the tip on the top. And we call that shear. So there is shear, but it's very low shear. If we went outside right here, we could stand on this lawn, especially here in Iowa, and not feel that there's wind. But if you want to fly a kite, for example, you get that kite up to 300 feet. It's really strong winds up there. And in the Midwest, we have what's called a low-level jet stream. That means you get up to 400 or 500 feet, you're seeing wind speeds that are dramatically different from what we're seeing just at 100 or 200 feet. It's well, you see it every time you fly out of the Midwest. You feel it every time you come up in an airplane at 500, 600, 700 feet. You'll always feel this bumpiness, and then you get up and above it. But that's how the Midwest is, and that's why it's so efficient to put wind turbines up out here. We can use wind turbines for base load in the Midwest because there are so many wind turbines over such a large area that it's windy almost, not almost everywhere, but it's always wind somewhere where there's wind turbines. So therefore, it can be used as base load, just like a coal-fired power plant or a nuclear or natural gas. It's not just, whoa, there's no electricity when the wind doesn't blow. Well, it always blows somewhere. And so we get clean, green power from that. And you may think that because we have 60 hertz on the grid, that it has to run at a constant speed all the time. But the rotor actually rotates faster the faster the wind speed, because you have something called an aerodynamic efficiency where the wind has to go through the rotor at 1/7 the speed of the tip going through. So it's a 1-to-7 ratio. And you want to keep that 1-to-7 ratio. At low wind speeds, you want to be more efficient. At high wind speeds, you don't have to be as efficient because there's so much power in the wind. The power in the wind is cubed to the wind speed. So it's an enormous amount of power. As you increase your wind speed, you increase the power dramatically. And so having the ability to tip these blades back at high winds and ensuring that you don't overspeed the generator is a technological advance that's come in just the last 25 years. In the beginning, we didn't have a way to pitch these blades. They were called stall regulated, and we had to, with a mechanical brake, stop them at high wind speeds. Today, everything is variable speed, and we deal with the variable frequency range on the controller converters in the bottom of the tower, so that the electricity that comes from the turbines can be directly implemented onto the grid. So we have, in the wind industry, we have something called a power curve. And that means that the more the wind blows, the more power will come out of the turbine. And because the power in the wind is cubed to the wind speed, you see the curve come up, 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 and then all of a sudden it increases almost logarithmically. And you don't pitch the blades, you want the blades to be as hard up against the wind as possible. So at 90 degrees on, well, depending on how you look at it, 90 degrees to the wind or at zero pitch. And then as you hit the maximum output of the generator can't take anymore. It's max, but you still want to produce power. So then you start feathering the blades back. They will just pitch back. And from about 5 miles an hour wind to about 22, 23 miles an hour wind, you're at full pitch. Yeah, so you're at 0% pitch. You're phasing the wind as much as possible. And then from about 22, 23 miles an hour wind, which is 12 meters per second, everything is metric in this business, we start feathering the blades back until the maximum wind speed has been reached, which is about 25, 26 meters per second, 50, 55 miles an hour. And at that point, there's so much load on the whole turbine that we decide to pitch all the way back and stop, because there's so much load that everything wants to start. It's called the overturning moment. Everything wants to start falling backwards. And the load from this rotation and from holding the yaw in place, and yaw means facing the rotor into the wind, all of that load has to transmit down through the tower into the ground somehow. And how do you do that? With a lot of concrete. We could dimension these turbines to run at 100 miles an hour wind. First of all, there's only a fraction of the amount of hours in the year where the wind is that high, so why dimension for that? If we over-dimension these wind turbines, your electricity is just going to be more expensive. And so there's this natural limit to how many hours. There's 8,760 hours in a year. How many hours are we at a certain amount of production on a wind turbine? That goes into figuring out, is it feasible to put wind turbines up somewhere or is it not? What will the power cost? What kind of power purchase agreement do you have to have in order to make it worth it for the investment? And the Midwest is prime for this.